Hello everyone, welcome back to all of you on my YouTube channel. I am Ankit Misra. I am teaching for the GATE chemical experience from last 5 years. Uh, I'm making this video for the motivation behind the GATE, keeping the motivation behind the GATE 2026 as well as BAR 2026. And also, this video will be very important for the person who is appearing for the Bihar Assistant Engineer examination for 2025 this year only, and they have opened the vacancy for the chemical engineers also. So this video is very going to be very helpful for those aspirants also, right? So, and before starting the video, I would like to request to all of you that those who have not subscribed my channel, please go and subscribe the channel, and don't forget to press the bell icon so that if I'm putting any new video, then you will be getting the notification for that. Okay, and don't forget to share in among your group, so that those people who cannot afford the this quality of education while paying the money, they can easily avail this kind of lecture free basis on my YouTube channel. Okay, so without wasting our time, let's just start with the process dynamics and control. So the subject is very important and very interesting. I'm damn sure about that. I'll make the subject very interesting, and you people will be very confident before writing the GATE examination in this particular subject. We'll solve lots of numericals that has been asked in the GATE and BARC, and some MCQ from Ram Prasad also on this particular channel, right? So when we talk about the process dynamics and control, so this is very crucial subject for the chemical engineers. And here you will see there is dynamics and there is a control. So the system is in dynamic mode. What is the dynamic mode? Means if a system is there, if a system is running, then the process parameter is changing with respect to time, and you are trying to read the, or you are getting the real time data for the particular parameter, let's say temperature, pressure, flow rate, and all of these things, so and so forth. And let's say if there is any abnormality that is being arises in the system, you want to control, and then you will be using a controller, and that controller will be working in order to reduce the error in the system. And how these things will happen, will be studying in the subsequent lecture. But here, in order to motivate you, why we are studying the process dynamics and control. So in order to ensure the safe and stable and efficient operation for the chemical process plant. So here you'll see, we'll study, it helps in maintaining the product quality as well as the optimize the process parameter variable like temperature, pressure, flow rate in the real time, right? So control system prevents dangerous instability. So let's say sometimes the system will become unstable, right, during running, because continuously 24/7 the system will be working. So there may be some kind of instability that will get arise in the system, but without intervening the manual operation, you want to handle the system, right? So if any disturbance is getting arise in the system, so that system can control all of these things, right? So that's why we are going to study about this process dynamics and control. As well as in some system, you'll see chemical engineering plants like aluminum smelter or a refinery, lots of flare smoke is coming, right? So in order to meet the environmental regulation also, this kind of process dynamics and control system is very much required. That's why this is the motivation behind this particular system, right? So before going to actual subject, actual topic, first I'll be talking about some fundamental things. I'll be giving you one example where you will see the flavor of why we are studying the process dynamics and controls, right? So let's say if we have a reaction A is getting converted into product B, having rate order of the reaction is 1 and rate constant is K, and I'm assuming this reaction is an exothermic reaction, right? This reaction can be endothermic, but right now I am assuming the exothermic reaction, and this reaction is happening in a continuously stirred tank reactor, right? So let's try to understand CSTR. So all of these parameters about CSTR you would have studied in chemical reaction engineering, and if you have not studied, definitely I'll be teaching you on this my YouTube channel, right? So now here you will see the reactant is coming and the reactant is outlet. So here if I'm assuming FA naught flow rate of reactant, and here flow rate of product A and B, and reactant FA and product is V. Now, since in order to control the temperature of the reaction system, because this particular reaction would be occurring at a particular temperature in order to maximize the product, so what will happen? You will see this reactor is provided with the cooling jacket, something like that. Okay, so something like that. There is a cooling jacket around the reactor. in which the coolant is flowing, right? Something like that with the wall, right? And I'm assuming flow rate of coolant is fc naught and flow rate of coolant here out is fc, right? Something like that. Okay, so this is the dynamics of the system. Here you will see, so when the reaction will start taking place, A is getting converted into B, what will happen? Temperature of the reaction system will change, but since this is CSTR, the temperature will be uniform. So here you will see the uniform temperature across the reactor at every location, because process parameter is not going to change inside the reactor, and also the temperature here will be T. But here you will see that temperature will be a function of time, means dt divided by dt we are not going to assume as 0, right, with reaction progress. But if you will apply the energy and mass balance, so what will happen? This reaction, let's say if reaction will proceed, what will happen? Temperature will get rise. If temperature will rise, since this is exothermic reactions, then the reaction will not move along the forward direction. In order to maximize the product, you have to extract some amount of heat from the system, so that the system will remain as it is at that particular temperature to optimize the product yield, right? So now in order to do so, what kind of things can be applied here? So you will use a controller system here, and temperature sensor, let's say TC1, and it will measure the temperature of the reactor, and also it will measure the another temperature control system will be there, that will measure the temperature of the coolant, right? Now this will be connected like that, and after that this will be giving a signal to this control valve, right? So let's say if temperature is increased more than what is the desired temperature of the reaction, so what will happen? This temperature controller will give a signal to this TC2, and it will get compared at this particular point. In future lecture I'll tell you how these things is getting regulated, and after that, based on the reaction temperature requirement, it will open the valve and close the valve in such a way that the product yield can be optimized, so that this flow rate will be getting changed, right? This is how this system is getting controlled. So what will happen, what you will see here, so in this system you have seen there is a process, and after you have seen there is a controller, and then there will be a measuring instrument, and then you will be getting an output, and here there will be a comparator. This is what the control system looks like, and this one is a temperature set point, right? This is what the temperature that is required for the reaction, and here you will set that T measured value, that is the output. Here you can see this is output, and this output is getting compared at this comparator, and after that, let's say this is minus and this is plus, so the error will be getting generated, that is equals to T set point minus T measured. So based on, if you will solve this particular loop, you will be getting that this error, the ultimate goal is to minimize this error, and if you are able to minimize this error, then the measured output will be at the desired set point, and where you will be running the reactor, and you will be getting the optimized value of the product, right? So this is how a control system works, and how this will work, how we are going to solve this kind of control system, that is closed loop, and what will the transfer function of process, controller, measuring instrument, and how these things will work, and how we can write the energy balance and mass balance, and coupled energy and mass balance in order to solve the system. We will be solving this. So before going to solve all of these things for the loop problem, this system is running in a dynamic mode. So you will be, when you will do the material balance, or when you are going to do a energy balance, you will be having a differential equation kind of thing, right? So in order to solve the differential equation in process dynamics and control, we are going to study about some methods, right? So let's say, if normally if you study mathematics, there you solve ordinary differential equation, and lots of methods are there, like Euler's forward backward method, RK4 method, RK2 method, and if you are going to solve this in MATLAB, ODE44 method is there, or if you are solving ODE in Python, there will be ODE in something like that. So but here we are going to solve the ordinary differential equation. So we will be having a particular method that I am going to teach you right now, that is called as the Laplace transform, right? This is very, very important for process dynamics and control. So why we are going to Laplace transform? The motivation is clear, that we are going to solve some differential equation, and in order to solve differential equation, we will be solving while using the Laplace transform, right? So in process dynamics and control, we have two things. There is a T domain and there is S domain. right? So I'll write these things in here, then this will be easy for. So sometimes we will be converting T domain to S domain, and sometimes we will be converting to S domain to T domain, something like that. Okay, so I think this is not very clear. I'll write, right, this thing is there. So when we are converting T domain to S domain, this is called as the Laplace transform, and when we are converting S domain to T domain, then we are calling it as inverse Laplace transform, something like that. Okay, so what we are doing in Laplace transform, so here you can write the definition. The Laplace transform of a function ft is defined to be fs according to the formula. So we have seen, we in Laplace transform we are converting T domain to F domain. So you will be having a function ft. So if I want to convert Laplace transform of ft, right, so that can be written as 0 to infinity and ft into e to the power minus st dt. So Laplace transform of ft will be called as fs. So you are converting T domain into F domain, and that will be equals to 0 to infinity and obviously ft into e to the power minus st dt. So this will be the formula that we are going to use. This is the master formula for converting T domain to F domain, and this is the Laplace transform, right? So now let's try to understand how we can solve. So if I am going to assume a simple case, that is very simplistic example. So if I want to convert Laplace transform of 1, so since here in this formula that ft is equals to 1, right? So now we know the formula of Laplace transform now. So I can write Laplace transform of 1, that will be equals to 0 to infinity, and ft is your 1 into e to the power minus your st dt. So that is equals to, if I'll integrate these things, I can write e to the power minus st divided by minus s, and we can write 0 to infinity. So that can be written as e to the power minus infinity minus e to the power minus 0 divided by minus s. So finally you will be getting 1 upon s. So the value of Laplace transform of 1, that is equals to 1 by s, and 1 can be written as also t to the power 0. So finally you can write Laplace transform of t to the power 0, which is equals to 1, which is equals to 1 by s. Is that clear? Now here the vice versa thing is there. Laplace transform of 1 is 1 by s. So if I want to write Laplace inverse of 1 by s, so that will be equals to 1. Is that clear? This is just a reverse case. When you know the Laplace, then definitely you will be knowing the inverse Laplace also. There is no any confusion. There should not be any confusion regarding that. This is exactly inverse of that, right? Now moving towards the next thing, let's say if I am converting Laplace transform of t only, right? So I can write 0 to infinity, and ft is your t now, e to the power minus st dt. So this is a formula, and this integration that you would have done in your class 12th standard only. So yeah, so you can use uv. So you have a method of solving this kind of integration, ILET. So in this method, inverse logarithm, algebraic, trigonometric and exponential function is there, and based on the order you take the priority of the function, and after that you can do the integration. So I'll do the integration t into 0 to infinity e to the power minus st dt minus obviously d upon dt of t into e to the power minus st dt, and 0 to infinity and obviously dt. So once you do the integration, you can solve these things like t into e to the power minus st divided by minus s, and 0 to infinity minus d by dt will get cancelled out, and finally you will be left with 0 to infinity into e to the power minus st divided by s. It will get positive, and again dt. Right, once you do the integration, then you can substitute the limit t into e to the power minus infinity minus obviously t into e to the power 0 divided by minus s, something like that, plus e to the power minus st divided by s square and minus s square and 0 to infinity. So once you solve this particular thing, you will be getting the value is 1 by s square. So finally what we have left is you have got Laplace transform of t is 1 upon s square, right? And similarly what I have told you, inverse Laplace if you want to write, so Laplace inverse of 1 upon s square can be written as obviously t. So both thing you can know, but I'll suggest you, if you know the Laplace, then definitely calculation of inverse Laplace transform would be very easy for you. So just be consistent with the Laplace, because this is just a forward kind of process. So and this is very easy and simplistic. So you inverse Laplace, you can just do the reverse. Okay, great. So now based on this kind of algebraic function, so I can write Laplace transform of t to the power n. So that can be written as directly factorial n upon s to the power n plus 1. So this is the formula where you can use this kind of formula for the algebraic function in terms of t to the power any function, and you can calculate the Laplace transform of these things. Okay, I hope this is clear to all of you. After that, I'll be moving towards the next example, and obviously lots of examples are there, and all of these examples are very much required for your GATE exam as well as cracking any exam. Also this will be very helpful for your semester examination also. So let's say now moving towards the next question, e to the Laplace transform of e to the power at. So if you will use this formula, formula number 3, that is e to the power obviously at into e to the power minus st dt. Now this is very simple integration you would have done in your class 12. So minus s minus a and t, and this is your dt. So once you do the integration of these things, you will be getting the value is 1 upon s minus a. I am not going to solve the whole integration, but you would be knowing. So finally you have got Laplace of e to the power at, that is equals to 1 upon s minus a. But here if I want to write Laplace inverse of 1 upon s minus a, so that will be equals to e to the power 8. So parallelly you have to do Laplace inverse as well as Laplace transform both. So once you know the Laplace transform, you must be knowing the Laplace inverse. Now moving towards the next formula, that is the fourth formula for today's discussion, Laplace transform of e to the power minus at. So that value will be equals to 1 upon s plus a. Similar the earlier question what I have done there. So you can use the same integration kind of thing and you can get these things, and again you can use Laplace inverse of 1 upon s plus a, that will be equals to e to the power minus at. So these kind of things, this is very simple, just integration thing, but the fundamental is this equations. If you remember this equation, this kind of equation, then definitely you would be able to solve this. Next formula for Laplace transform is, let's say, Laplace of sin at. So that will be equals to a upon s square plus a square. And again if I want to write Laplace inverse of obviously a upon s square plus a square, so that will be equals to sin at. Is that clear? Next formula can be written as Laplace transform of cos at, that can be written as s upon s square plus a square. And again I can write Laplace inverse of s upon s square plus a square, that can be written as cos at. Is that clear? Okay, so this is very simple. You have to remember these things somewhere anyway, but a fundamental formula already I have described you. You can go through the fundamental formula and you can again solve this particular thing. Now coming to the 7th formula, let's say sometimes they will ask you Laplace transform of e to the power at into sin bt is what. So here you can see there are two functions, e to the power at and sin bt. So you know Laplace transform of what is e to the power at, that is equals to 1 upon s minus a, and Laplace transform of sin bt, you know that is value of b upon s square plus a square. But here there is a combination of this function as well as this function. So if you will combine these things, so only in this formula you have to substitute, s will get substituted by s minus a, something like that. So directly now I can write Laplace transform of e to the power at and sin bt, that can be written as this is b, right, because the coefficient in sine function will come here. So that is b upon obviously s minus a whole square plus b square. And what is a? A is the coefficient on the exponential function, right? So this is how you have to remember. But again, how this is coming? This is coming from your fundamental formula that I have discussed earlier, right? Again, if I want to write the formula for it, let's say Laplace transform of e to the power minus at into sin bt. So now you know Laplace of e to the power minus at. So directly I'll be writing these things is like obviously b upon s plus a whole square plus b square. Now moving towards the next formula for ninth number, let's say. So Laplace transform of e to the power at and cos bt. So similar to sine function, you can write the for the cos function also. So I can write here s plus, sorry, if it is plus, then you have to write here is minus, because you have seen these things, s minus a divided by s minus a whole square plus b square. Is that clear? And again, similar thing, if you want to write this formula, let's say 10 Laplace transform of e to the power minus at and obviously cos bt. So that can be written as s plus a divided by s plus a whole square plus b square. So these are some very important formula. And in actual numericals, you will see either if you'll solve previous year gate question or bar question, and especially assistant engineer for Bihar, so you will be getting these kind of things, right? So again, I am not going to solve lots of numericals over here today, but I'll be solving only the formula. So these are where the fundamental formula that is very much required to solve any kind of questions in the process and control on the Laplace transform. Now I'll be talking about the transform of derivative, because ultimately we are going to solve the differential equation. Transform of derivative. So how does derivative looks like? So let's say you will be having a function ft. So if I'll do d of ft by dt, so this is the derivative of the function. And what I want to do, I want to calculate the derivative of the function, right? So Laplace of derivative of ft divided by dt is equals to what? So we are going to solve these things, right? So let's say how we will be solving this thing. So in order to solve these things, already I have told you Laplace transform of ft, that is equals to obviously 0 to infinity and e to the power minus st into ft dt. But here your function is this one, right? So finally, if I'll write Laplace of d of ft divided by dt, so I can write 0 to infinity and obviously d of ft divided by dt into e to the power minus st. Is that clear? And dt. So now here you will see again you can use the integration by parts, because this is the integration of two functions. So you can use integration by parts, right? So let's say if I will be assuming the value u is equals to e to the power minus st and v equals to let's say dft divided by dt, something like that. Is that clear? So the value of dv will be equals to dft by dt into dt, right? Now if you want to solve this kind of integration u dv, so the integral will be equals to uv minus integral v du, right? So this is the formula that you would have studied in your class 12th standard only. So this is the formula. So I'll be using this formula, that u dv equals to uv minus v du. So u is this one and dv is this one, right? So let's try to understand how we can solve this particular thing. So if I'll substitute this value in the integration, so we have dv is equals to df divided by dt into dt, right? So if I'll substitute these things 0 to infinity and obviously df divided by dt into e to the power minus st dt, so that can be written as ft into e to the power minus st and 0 to infinity minus 0 to infinity and obviously ft into minus s into e to the power minus st dt, exactly in the same way that I am writing here, right? So if you'll expand these things and if you'll substitute the limit of integration, we will be getting ft into e to the power minus infinity minus f0 into e to the power minus 0 plus s into fs. So this value would be equals to 0. So finally you will be left with s into fs minus f0. So finally what we are getting, Laplace transform of d of ft divided by dt, this is a differential, that is equals to s into fs minus f0. Is that clear? So the first what you have to do, so you will be having a function ft, so you will convert this into fs. Once you have converted, you will substitute this, and after that you will substitute s is equals to 0 and you will be get t equals to 0 and you will be getting these things. Is that clear? So lots of things will be there where you will be seeing these things. Now again, this is the first order differential. Now if you want to solve Laplace transform of, there will be d2 ft divided by dt. So in the same way you can use this formula, that 0 to infinity and obviously d2f divided by dt square into e to the power minus st dt, and the derivation would be a bit lengthy, that is not required here. So I am just directly going through the final results of this particular thing. So directly you can write s square fs minus s f0 minus f dash 0. So Laplace transform of d2 ft divided by dt square, so this will be this one. Is that clear? Okay, I hope this is clear to all of you. So this is how this differential Laplace of differential things works. So here you can see there is a trend. If the Laplace of first order derivative was s into fs minus f0, Laplace of second order derivative of function ft, that is s square fs minus s f0 minus f dash 0. So if you will see, there is a trend that is being associated with this, or that is there is a trend which is being followed over the differential. So I can directly write Laplace transform of nth order derivative dn ft by dtn. So let's say if it is third order derivative, fourth order derivative, you can use this formula, and directly I can write s to the power n fs minus s to the power n minus 1 f0 minus s to the power n minus 2 f dash 0 minus s to the power n minus 3 f double dash 0, and so forth. Finally f to the power n minus 1 0, something like that. Okay, so this should be the formula for your nth order derivative, something like that. So I won't suggest you to remember these things, but mostly they will ask you any questions on the basis of second order derivative. But again, nth order derivative is being required, but sometimes it may be possible they can ask you in the MCQ that which of the following options are correct for the Laplace of these things. But here you have to assume, here you have seen that f dash 0 were there, right? F dash 0 were there. When f dash 0 is in the last, means when order was 2 minus 1, that is equals to 1. That's why if nth order is there, then n minus 1, that derivative will be coming. And what is f0? When you are substituting t equals to 0. At t equals to 0, it means initial value of this thing. Is that clear? So this is how these things can be solved. Okay, I mean in subsequent lecture we will be solving lots of numerical on this particular topic as well, but here I just solve only the topic. And also in the next lecture I will be talking about the partial fraction also. So let's say in integration we would be doing the integration by parts. We were calculating the integration using partial fraction also, right? So in Laplace transform also you will require to understand how to do the partial fraction of any fractional function, and based on that partial fraction we can calculate the Laplace transform. Okay, so with that I'd like to end the lecture here only. In the next lecture I'll be talking about some more complicated Laplace transform of this differential function, and we'll solve some numerical one, how to solve the differential equation using this thing. So you would have get the flavor of why we required this Laplace transform, because a Laplace transform gives you the value of the differential, first order, second order, and nth order differential. And in a differential equation we see there is a differential, right? Second order differential equation will contain higher order of differential of 2, First order differential equation will contain higher order of differential function of order 1, and nth order differential equation will contain higher nth order differential something, so differential function in the equation. So this is how you will be having a differential equation, and we will be substituting this value in place of this, and we will directly calculate the function in terms of fs in terms of s domain. And when we convert we have fs, then we can convert use Laplace, and again we inverse Laplace, and we can calculate the t domain of the function. And at any particular time, that is we can calculate the dynamics of the system. Let's say in temperature, pressure or flow rate, we can calculate the value at any particular time while using the Laplace transform. Okay, I hope this is clear to all of you. See you in the next lecture. Thank you very much.